Hello, this is the Section 8.5 lesson. In Section 8.3 we talked about calculating the test statistic for a claim about a population proportion. In this section we're going to focus on testing a claim about a population mean. For this lesson you're going to need your calculator. To illustrate this process, let's look at this example. A manufacturer of shredded cheese claims that the mean weight of all of its 12-ounce packages of shredded cheddar is greater than 12 ounces. To test this, they select a sample of 150 packages, weigh them, and find the mean weight as 12.05 ounces with a standard deviation of 0.15 ounces. Now, at first glance, our data may seem to prove the claim. But remember, the claim is made about the population of all 12-ounce packages of shredded cheddar. Our data comes from a sample of those packages. In that sample, the mean definitely is greater than 12 ounces, so it does appear to support it, but we need to analyze just how strong that support is. Is it very strong so that we can conclude that the claim is true, or is it just very weak support? Well, here's our claim. The mean weight of these 12-ounce packages of shredded cheddar is greater than 12 ounces. We need to first define our parameter. Notice our claim is about a population mean, so our parameter is mu. It's the mean weight of all 12-ounce packages. Again, we stress the word all because we're making a claim about the population, not just the sample. Okay. Claim in mathematical notation is that mu is greater than 12. If false, mu is less than or equal to 12. The null is that mu equals 12, and the alternative will be the original claim that mu is greater than 12. Next, we need to calculate our test statistic, and here's our formula. We're not going to talk about where this formula comes from, but this formula is used for a claim about a mean where our population standard deviation sigma is not known. If we somehow know the population standard deviation, then we would use concepts from Section 8.4. But that's rarely the case, so we'll skip that section and just use this formula. Notice it's t equals, so our test statistic is a t-score, it's not a z-score. That's a big difference from the previous section. You take x bar minus mu naught divided by s divided by square root of n. Mu naught is the mean used in the null hypothesis. X bar is our sample mean, which comes from our data. S is our sample standard deviation, which again comes from the data, and n is our sample size. So note that we need two things from our data, x bar and s. In the previous section we only needed one thing from our data, that was p hat. So if we were to use this formula, we'd plug things in like this. X bar is 12.05, mu naught is 12. S is 0.15, N is 150. We plug that in and we get 4.08. Now we're not ever going to use this formula. We're not going to plug things in manually. We're going to let the calculator do the work. We'll illustrate that here in a minute. Now to calculate our p-value, our p-value would be the area to the right of our test statistic because this is a right-tailed test. However, big difference is that our curve here is a t-distribution curve. It's not a bell curve. T-distribution curve looks very similar to bell curve, but they're not identical. So that shaded region there would be our p-value, but we don't have a table for area underneath the t-distribution curve, and so we're going to use our calculator to do all the work. Now the command here is stat test option 2 for t-test. This test is simply called a t-test because our test statistic is a t-score. And it's going to ask for four things. First, mu naught, which is the mean used in the null hypothesis, and then x bar, which is our sample mean, sx, which is the sample standard deviation, and n is our sample size. Okay. Now you see there on the upper left the command option 2 for the t-test. When you hit enter, you'll get a window that looks similar to that right below it. Top you see t-test. Next it asks for input, and we have two options, either data or statistics. If we have our raw data, we can enter it in a list and then simply enter the name of that list and it'll calculate our sample mean and standard deviation for us. But that's not what we have here. We have our summary statistics, so we'll choose statistics, and then below that we enter mu naught, x bar, sx, n. which all comes from our data given in the problem. And then thirdly, it asks for the form of our alternative hypothesis. Either mu is not equal to mu naught, mu is less than mu naught, or mu is greater than mu naught. In this case, the alternative is that mu is greater than 12, so we'll choose that third option. And then below that, we choose either calculate or draw. We'll just choose calculate, hit enter, and we get a window that looks like that in the upper right hand corner. Notice it says t-test. Below that, we have our alternative hypothesis, mu is greater than 12, which is identical to our alternative hypothesis, which means that we entered things correctly. Below that, it gives our test statistic, 4.08. Below that, it gives our p-value. Now, our p-value here is in scientific notation. It's 3.6 times 10 to the negative 5, which means in decimal form the p-value would be 0.00036. We have 4 zeros in front of the 3. What that really means, we have a very small p-value. Below that, we see x bar, sx, and n. Again, we can use those numbers to verify we entered things correctly. So the important thing there is the p-value, 0.00003. The exact value really isn't important. It's a very, very small p-value, and so our technical conclusion would be to reject the null hypothesis. Really doesn't matter what our significance level is, we're going to reject the null hypothesis. Okay. Now we word our final conclusion the same way. We'll use this flow chart. The original claim did not contain equality, so we go down. Do you reject the null hypothesis? Yes, we do. So the sample data support the claim that the mean weight of all 12-ounce packages of shredded cheddar is greater than 12 ounces. Okay. So our sample data did appear to support the claim, and that level of support was indeed great enough for us to conclude that the claim does indeed appear to be true. What this conclusion means in even less technical terms is that the packages do not appear to be underfilled on average. On average, it appears that the weight is greater than 12 ounces. Now that doesn't mean that every single package weighs greater than 12 ounces. It just that means that on average they do not appear to be underfilled. Now the requirements to use this formula are: number one, the sample is random. Again, that's always a requirement. Second, the value of the population standard deviation is not known. If we were to somehow know the population standard deviation, we would use concepts from section 8.4, but that's rarely the case. And then third, either the population is normally distributed or n is greater than 30. Now in this case, n is 150, so we meet this second part of this third requirement. If n is less than 30, then we need to somehow determine if our population is normally distributed. If it is, then we can use this. So that's it for this section. The Course Compass homework is titled Section 8.5.